Let's see what is Fleming's left hand rule. So take out your left hand, and you take the thumb, take the index finger, and take the middle finger. Point it out like this, such that they are all mutually perpendicular to each other. That is, you have 90-degree here, 90-degree here, 90-degree here. Don't keep it anyhow. Don't keep it like this. Keep it this way. The other two fingers you can curl it in. All right. No need to put the tape, or you don't have to write on your hand or anything like that. This is I'm doing only for you to remember and understand, only for that purpose. Otherwise you don't have to write this on your hand. Okay, so what does Fleming's left hand rule says is this: the index finger shows you the direction of magnetic field. The index finger shows the direction of magnetic field. The arrow pointing like this means magnetic field will go from north to south like this direction. All right, the middle finger points the direction of the current. Middle finger points the direction of the current, and the thumb points the direction of force. So when I place it like this, all right, you'll see all are mutually perpendicular to each other. Now how do we use this? It is used like this. Let's say you have a current carrying conductor. Let's say you have a current carrying conductor where the conductor is coming from the board and is coming towards you like this. All right, and you have the current flowing in this conductor towards you. That means the current is coming out like this. When the current is coming out like this, all right, we are not looking into its magnetic field. What we'll do is we'll place one magnet on this side and that side. So let's say from north and a south pole we place it. All right, so the direction of the magnetic field will be how? The direction of the magnetic field will be from north to south. So let me draw that magnetic field for you. We have, let's say, one magnet north this side and one magnet south. So the direction of the magnetic field would be this direction. All right, and let's say the conductor is coming out from this. It's coming out like this. All right, in which the current is going from this end to this end, from the board towards you. All right, so what do I do now is I hold my finger. So if you see, I'm holding the index finger in the direction of the magnetic field. The current in the conductor is coming out. I place it like this. So what does this show is this: so when I place this current carrying conductor in this external magnetic field, there will be a force experienced, and the direction of the force will be in upward direction. The wire will start moving up. It will move up. That is what your Fleming's left hand rule says. So now let's say if I change the direction of the current and the magnetic field. All right, so let's say I have a current carrying wire like this, where the current is, let's say, going downward. All right, where the current is going downward, what I'll do is I'll take my left hand, point this finger, the middle finger, in the direction of the current. Since the current is going downward, I'm pointing it down. All right, and then I have to see what is the direction of the magnetic field. Let's say the direction of the magnetic field is coming towards you. All right, then what do you see? The thumb is pointing towards left. The thumb is pointing towards left. So what will happen? This wire will start moving towards left. All right, so let's put this in a live example and let's have a look. All right, so what we have a battery eliminator, then we have the copper wire, and I have a magnet. All right, the magnet has a north pole on this side, so the field is coming out this direction. The positive terminal is here, so the current in this wire is going this direction. So if I ask what is the direction the current in this wire is, outward, it is coming towards you. All right, what is the direction of this magnetic field? It's coming this side, that is towards your right. So this becomes your external magnetic field. This is your current carrying conductor. So right now what I have done is I have placed a current carrying conductor in an external magnetic field. So when I switch on the current, the statement will be true, and when I switch it on, this wire will experience a force. The force which is experienced will move the wire. So we need to find out what is the direction of the force. So let's use our Fleming's left hand rule. So what we have from a left hand rule is this. So what I'll do now is I'll point my finger, that is the middle finger, which points the direction of the current, in the direction of the current. The direction of the current is this way only, so I'll point it like this. All right, okay. Then I can even point like this, I can even point this way, no issue. All right, so once this is fixed, I cannot change this. Once the direction of the current is fixed, I cannot change this way. All right, for example, the magnetic field now is going out this side, correct? The magnetic field now is going out this side. This is the north pole, it's going out this side. So to do that, I cannot say out like this, because the index finger shows the direction of the magnetic field. If I do like this, what happens is I am changing the direction of the current. So once I fix one quantity, the other quantity I have to move, and not the quantity which I fixed. So I'll start again. Direction of the current is coming out, so this is the direction of the current. The direction of the magnetic field is going that direction, so this is also fixed. I don't move it, I don't have to move anything now, because these two are known to me and it is fixed. The result of this, what I get from this is the direction of the force. So direction of force is what? Upward direction. So what we should see in this experiment is, when I switch on the current, the wire should move upward. So let's have a look at this. I'll do it twice. Alright, here we go. Did you see the wire going up? Yeah, I'll do it one more time. Have a look. There you go. Alright, so that is our Fleming's left hand rule. Now what we can also do is, I can change the position of this magnet. Alright, so let's change the position. So let me bring it in this direction. Right, now think and tell me, what is the direction of the current? It's coming out. So let me fix it. Direction of the current is fixed. Now what is the direction of the magnetic field? Is it still going out that side? North is over here, the field is coming out. Now see, the field is from here, is coming out like this, and then it is going back over here. So will you be taking this magnetic field over here? No, we have to see the magnetic field that is interacting with the current carrying wire, not somewhere else. Like for example, if I take one magnet and place it over here like this, and this will have its own magnetic field. Right now the direction of the magnetic field of this magnet is coming out like this. I will not take that direction. Why? Because there is no current carrying conductor placed in that field. It has to be in that range. So back to our example, the direction of the magnetic field is now what? Towards your left. So what do I do now? Towards my left. So do I do like this? No. Alright. So direction of the current is still outside, magnetic field is this side. So I have to turn my hand by keeping the current direction constant, fixed, and I get like this. Alright. Now what do I get? The thumb is pointing downward. Thumb is pointing downward, which means the wire will experience a force which will push the wire downwards. Alright. So let's have a look at that. Here we go. It goes downward. Correct? Let me do it again.